Okay, so this time I'm going to be making apple crumble, and I'm going to do it the right way, which means using the theory of symmetric monoidal categories. So symmetric monoidal categories are very general structures, and they have a really fantastic feature that means that we can visualize lots of the sort of behavior that's going on in these kind of structures using these sorts of wiring diagrams. Okay, so here's a picture of our wiring diagram for making apple crumble. So you can see that we're going to start with these different inputs here. We need a cold oven, 60 grams of sugar, 100 grams of flour, 60 grams of butter, a mixing bowl, a tablespoon of sugar, an apple, a knife, and a baking dish. And then we're going to do these different operations. So I'm going to get into the category theory later, but for now we can sort of appreciate at least what this means in a sort of intuitive way. So for example, we take our apple and our knife, we peel and slice, and we get a prepared apple, and we also get our knife back out. The other thing we're going to do is take these ingredients and we're going to sort of mix them and rub them up and get our sort of breadcrumbs in a bowl. We can also convert a cold oven into a hot oven by heating that oven. And so after we've done these things, we can do these other kinds of processes like putting these things in dishes, mixing them together, and then finally cooking. And then we're going to get our delicious apple crumble in a dish out. And we're also going to get out the hot oven and also the mixing bowl and the knife. It's kind of nice to represent what's going on with a diagram like this. I mean, this is more like the kind of flow diagrams that people have been making for ages. But with this kind of idea of symmetric monoidal categories, we can really use these kind of diagrams. We call them wiring diagrams, and we can use them in a very kind of precise way. Peel is kind of like a function. We put an apple and a knife in and we get a peeled apple and a knife out. And then we have this slice operation, which takes in these two inputs, and it's going to give us out our prepared apple and knife. And also we have this sort of idea of composition. So we can basically form a sort of bigger box that's representing all of the things that are going on in here. Okay, so let's perform this peel function then. So we have these inputs, a pair of an apple and a knife, and now we're going to perform this peel function, and hopefully as an output we're going to get a peeled apple and a knife. So let's now evaluate this function. Now, another thing that I didn't actually represent in this kind of picture here is that we actually get another output when we do this peeling. So in addition to getting the knife and the peeled apple, we also of course get the apple peel. And so if we're really being precise, that would be another kind of output of this function. And so now we've got our peeled apple. There it is. And we've got our knife. And so now we're ready to apply this second kind of function, which is going to change these inputs into a prepared apple and a knife. So now let's evaluate that function. So we take this pair of inputs and now let's convert them into a prepared apple and a knife. Now there are lots of details, of course, about how to actually cut up the apple. And I've just realised there's also going to be another output because there's going to be part of this apple that we actually want to discard. And so there we are. Now we have our outputs, our knife and our prepared apple. And then we also have this waste apple, which is some extra stuff which we could have added into our diagram. And we also have other things like the bowl, the table, myself, the universe, etc. that are also necessary. But I do think it's a good thing that we can draw these kind of diagrams and sort of capture the kind of main details that you'd want to tell somebody when they're cooking. And so the normal way we might represent something like this using category theory would be as a sort of diagram like this. Okay, so these objects here, these dots, these are representing sets, and then these arrows are representing functions. And this kind of circle times thing, we can think of this as the Cartesian product. So what this basically means is apple producted with knife. So we can think of apple here as representing the set of all apples, and knife represents the set of all knives. And so what this product means is this is the sort of Cartesian product of the set of all apples and the set of all knives, which means that we can think of this object as the set of all pairs of an apple and a knife. And then we have this peel function, and that's going to send any particular pair of an apple and a knife to a peeled apple, and the knife as well is going to get returned. So we put an apple and a knife in, and we get a peeled apple and a knife out. And that's the peel function. And then we can compose this with the slice function, and then we're going to get our prepared apple and our knife out. So that's fine. However, it's kind of nice to represent what's going on with a diagram like this. Okay, so the rough idea of these kind of wiring diagrams is that each of these wires is representing an object in our category. So in our case, this is the set of apples and this is the set of knives. And then these boxes are just representing our functions. But the clever bit is that in these kind of symmetric monoidal categories, we have some notion of being able to take the product of things. In our case, this is Cartesian product. And when we write one wire on top of another one, we can think of that as representing the sort of product of those two objects. So more precisely, we can interpret this as saying that the input of this peel function is something from the product of apple and knife. And then the output is going to be something of a form of product of peeled apple and knife. Okay, so here's the sort of big wiring diagram, which is sort of representing the whole process of making this apple crumble. You can see that we have this idea of doing things in parallel. Okay, so if we're being really literal about this from a category theory point of view, each of these kind of wires is representing an object. So in a sense, it's representing a set. So when we say a tablespoon of sugar, we really mean this is sort of the set of all tablespoons of sugar. And so we have these different sorts of things that we have to start with. And what we're really starting with in real life is a sort of element of the product of each of these sets. So in other words, we're going to start with a particular baking dish, a particular knife, a particular apple, etc. And then we have these different operations that we're going to do. And so this is really the idea that when we have a kind of tuple, so when we have, like, let's say a pair of things, then we might do one function on the first entry of the pair and another function on the second entry of the pair. And then we end up with a pair of outputs. So that's kind of like the idea of doing two kind of functions in parallel. And in a sort of similar way, you can see that we can think of this as doing sort of these boxes in parallel. Although we can see geometrically that it doesn't really matter if we sort of slide these boxes to the left or right. I mean, if you think about this as time going on, it doesn't really matter if you do your peeling and your slicing before you heat your oven to 190 degrees, or if you heat your oven up first and then do your peeling and slicing. The output's going to be the same, provided that you follow all the kind of instructions here. And so we've already done this sort of step. We've done our peeling and slicing. So now let's do this stage here. So we're going to heat up our oven. So what we need is a cold oven. So there's a cold oven. And now we're going to change it into a hot oven. And to do this, we need to make our oven heat up to 190 degrees. So there we are. We've applied this peel and slice function. We're in the middle of applying this heat to 190 function. Okay, so the next thing is we want to get this kind of crumbly breadcrumb sort of mixture. So what we need to do this is we need a mixing bowl and we need some butter. I'm using about 60 grams of butter, and we need some flour. So it's about 100 grams of flour there, and about 60 grams of sugar. And so we're going to sort of do this function, which is going to take these inputs, and hopefully it's going to output this kind of breadcrumb mixture, which is then going to be in this mixture bowl. So we've got our inputs, and so let's evaluate. We're going to be adding these different ingredients into this bowl. And then sort of using hands, we're going to mush it up to get this sort of breadcrumb-like consistency. I'm not exactly a Michelin star chef, so I'm not sure what good a job I'm going to do, but here we are. So of course there's lots of details of this process which are not recorded in the diagram again. And so again, I think trying to represent these sort of real world ideas using things like category theory can be really good for the theory as well, because there's lots of things that you're doing that you then think, well, how do I actually represent this theoretically? And there we have our output, our sort of breadcrumbs, which are going to be in this bowl. So now we've applied this step here. We've taken our mixing bowl, our butter, our flour and our sugar. We've applied this mix and rub function, and now we've got our breadcrumbs in a bowl. Okay, so this is going to be the next box that we want to apply. So we're going to need a tablespoon of sugar, which we have here, and our prepared apples that are here. And also we're going to need our baking dish that we have here. And so now we're going to combine all these things, applying this put in dish thing. And our output's going to be our sugary apples in a dish. So let's do this now. And so there we are. And now we're going to apply this box here. So we need our sugary apples in a dish and our breadcrumbs in a bowl. And then what we're going to get out is our uncooked crumble and also our mixing bowl. So here are our breadcrumbs in a dish. So we want to be emptying these out. This is probably where having some actual experience doing cooking would come in useful, because I suppose we want to get this crumble mixture to be covering up the apples, but I suppose this is what happens when somebody who's only cooked once in the last 5 years tries to make a YouTube video about cooking. Anyway, now we have our mixing bowl and our uncooked crumble. And remember, we also have our knife somewhere. Here it is. That's come along for the ride. And of course, we have our oven, which is now hot. And so the next step is going to be to apply this box here. So we need to combine our uncooked crumble and our hot oven, and then apply this, cook for 30 minutes or maybe 45 minutes. And then we're going to get out the apple crumble in a dish and the hot oven. And of course the mixing bowl and the knife are also going to come along for the ride. So let's now evaluate this cooking function. There are the inputs, and let's see what the output is. And so now, after all that complex manipulation of symmetric monoidal categories, we can enjoy the final outputs of our morphism, some delicious apple crumble. The benefits of category theory. Okay, so now we've got our crumble, let's understand more about the theory. And so these symmetric monoidal categories have been described, for example, by John Baez as a sort of Rosetta Stone through which lots of different subjects like physics and engineering and ecology and chemistry and electronics and computer science and logic and on and on and on. It's a place where all of these kind of subjects can meet and understand each other, because basically these kind of wiring diagrams that we've been looking at have a great amount of sort of expressive power, and they're kind of an idea which I think we sort of naturally, almost subconsciously appreciate. And it's just so cool that we have this kind of very, very concrete theory which we can connect to that. And it basically means that someone who knows about symmetric monoidal categories can go to all these different disciplines and instantly kind of appreciate like the connections between them. And so I basically want to get us to a place where we know the definition of symmetric monoidal categories and sort of understand how it all fits together. So we're going to start off with monoids. A monoid basically is a category of one object, and then we're going to go on to monoidal categories and then symmetric monoidal categories. So now let's start the more kind of theoretical portion of the video. If you get lost in the terminology, you can always go back and look at my videos on functors and natural transformations from earlier in this kind of category theory for beginners playlist. And also, before I go on, I want to make it clear that this example of kind of using cookery to represent what's going on in category theory wasn't really my idea. Brendan Fong and David Spivak use these kind of wiring diagrams to represent what's going on in cooking in their wonderful book 7 Sketches. And Eugenia Cheng also likes to introduce ideas in category theory using these kind of examples from cookery. Okay, so I'd like to talk about monoids and monoidal categories, and basically have a kind of monomaniacal Monday where I talk about all things mon. So let's start with the idea of a monoid. So what is a monoid? Okay, so I've written the sort of long definition of a monoid up here, but to tell you quickly, you can just think of a monoid as a category that has a single object. But let me tell you the sort of traditional view of a monoid, because one of the things that we're going to be doing in this video is really looking at this idea of a monoid from lots of different angles, and it's a very rich kind of idea. So the sort of traditional view of a monoid is that it's a set with a binary operation, which means that we have some sort of operation where we can load in two different kind of elements of the set, let's say X and Y, and then we can get out another element, which we might call X after Y. And this kind of operation has some sort of special properties. In particular, it's an associative operation, which means that this kind of equation always holds for any X, Y, and Z. And also we have this special kind of element of the set called I, which is kind of like the identity. So we have these kind of rules that composing or multiplying an element by I just returns that element back again. And so that's what a monoid is. And a great example is the natural numbers. Okay, so we have these natural numbers 0, 1, 2, 3, and so on. And we have this sort of binary operation where we can take in a couple of natural numbers and get a new one by adding them together. So if we operate on 2 and 3, then the output would be 2 plus 3 equals 5. And then our kind of unit would be 0 in that case, because adding 0 to any natural number just returns that natural number. And it doesn't matter if we add it on the left, if we add the 0 on the right hand side or the left hand side. And so that's an example of a monoid. So this is the sort of more, I suppose, classical view of what a monoid is, but it's nice when you know category theory that you can think of a monoid in a much more kind of compact way as just being a category of one object. So in what sense is that true? Well, just take a category of one object and then look at all the arrows from that object to itself and think of that collection of arrows as your set S, and think about arrow composition as this kind of binary operation. So we can take any sort of pair of arrows which are going from our object to itself, and then our sort of operation where we get a new kind of arrow is just composition. Okay, so we could, for example, in this case, I've labeled these arrows kind of suggestively, so we could compose this arrow 1 here with this arrow 2, and we could imagine that that composition yields this arrow 3 here. And so we can basically cook up a sort of category which has one object, but it has loads of arrows from that object to itself, and the way that we compose those arrows ends up looking like adding together natural numbers. So that's basically what a monoid is. Okay, so now let's introduce the idea of monoidal categories. Well, I'm start with the idea of a strict monoidal category because it's a bit simpler. So firstly, let's just recall our definition of a monoid. Okay, so remember a monoid basically consists of a set, let's say S, and a kind of binary operation. So that's a function that takes in a couple of values from that set and returns another value. And also we're going to have a special element of that set, which we call I. And we want this kind of setup to be such that this kind of multiplication, in air quotes, this operation here, this dot operation, is associative. So we have this condition. And also we want this kind of I thing here to act like an identity. So when we do this kind of multiplication of I with another element X, we get that other element X back. So that's the idea of a monoid. And then a strict monoidal category we can really think of as a kind of categorification, if you like, of this idea of a monoid. And so basically, if you think about a category which only has identity arrows, then that category is kind of like a set, right? If you just imagine a picture of one, we have this category and it has, say, lots of objects. But let's say each of those objects just has an identity arrow. Well, then really that category is just acting like a set, right? All we really have is a bag of objects, a set of objects. And basically, we can then think, well, what if there was a sort of monoid structure on that set? What if there was a sort of binary operation and so on, satisfying these kind of conditions? And then we could say, well, could we then actually generalize that kind of idea so that what if there were actually some non-trivial arrows in this category? In that case, maybe we can make a definition that's a sort of generalization of this kind of idea of a monoid to a sort of category which doesn't just have like elements or objects, it also has arrows. Okay, and that's kind of what the idea of a symmetric monoidal category is. So if you look at these kind of descriptions side by side, you should hopefully see that there's a lot of similarity. Rather than having a set, we have a category. And rather than just having this kind of binary operation, this function that takes in two inputs and gives a single output, we now have a functor that takes in two inputs and returns an output. I'll talk about that more momentarily, but we call this functor either the monoidal product functor or sometimes the tensor product functor. But the idea is that it can take in a couple of objects and return an object, but it could also take in a couple of arrows and return an arrow. And we also have a special kind of object in our category, which we call the unit object. And then we also want this kind of functor to satisfy this kind of associativity and we also want this kind of monoidal product to satisfy this kind of associativity condition. And also we want this kind of unit object to act like the unit works for a monoid. So if we do the tensor product with a unit, either before or after, we just get the original thing back again. And so that's basically the definition of a strict monoidal category. I'll come back to this again very shortly. But let me just talk a bit about how we can think about this functor here, this monoidal product functor. So as a functor, the idea would be that the inputs, so since this is a functor, the idea would be that the inputs might be an arrow f from an object A to an object B in our category C. We might also have an object A dash and an arrow F dash from A dash to B dash. And so that kind of pair of those two arrows might be the inputs to our functor. And then this functor is going to send those to a new kind of thing. And that's going to be an arrow from A tensor product A dash to B tensor product B dash that we could call F tensor product F dash. So that's kind of how this functor works. And indeed it has to be a functor, so there are various kind of things that follow from that. So let's have a look at a nice simple example of a symmetric monoidal category. It's this category where the objects are just these natural numbers, so these non-negative integers, and then we're just going to have one arrow from one object to another when the first number's less than or equal to the second one. So the arrows are just kind of indicating size ordering. And so this is going to be a partially ordered set. And then we can have an idea of tensor product. So we could say that the tensor product of a couple of numbers is just the sum of those numbers. And we can take our unit to be 0. And so it's quite a good exercise to check that this really does give us a strict monoidal category. For example, we can see that this kind of condition is true because if we have numbers A, B, and C, then A plus B plus C is equal to A plus B plus C, and so on. So we have this definition here of strict monoidal categories. Now, it turns out that this condition is a little bit too restrictive for kind of a lot of structures that we're interested in. And so what we like to do is actually relax this definition a bit. So rather than having equal signs here, we instead would prefer to sort of relax this definition and just say that we require these kind of things to be isomorphic in a particular way. And we basically call the version of this concept where we make that kind of relaxation a monoidal category. Now I'll go over the proper definition momentarily. Okay, so now we finally get to the definition of a monoidal category. So this is something in category theory that's really well worth putting some time into thinking about, because especially with a lot of sort of modern developments in applied category theory, this idea of a monoidal category is becoming really quite central. So you can think of this as a sort of weakening of the idea of a strict monoidal category, but let me describe what's going on from first principles. So a monoidal category is where we have a category C and we have this functor, which we can call tensor product or monoidal product. And so it takes in a pair of things and outputs another thing in our category. Of course, as a functor, it is defined on pairs of objects, and it's also defined on pairs of arrows. And we also have this special object I, which is our unit object. But now we also have these extra things, and we can think of these as sort of families of morphisms, families of arrows. Really, they're defining natural transformations. Okay, so basically for every triple of objects A, B, and C, we have this arrow alpha A, B, C, and this is going to be an arrow from A tensor product B tensor product C to A tensor product B tensor product C. Okay, now actually alpha is going to be a natural transformation, and so this is the sort of component of alpha associated with objects A, B, and C. And in fact, alpha is really a natural isomorphism. So this is really going to be an isomorphism between these two things. And so if you think about this example from sets that I was talking about before, where we can sort of have three elements written like this or three elements written like this would be an example of using this kind of natural transformation components, alpha, A, B, C. And so we actually call this natural transformation alpha the associator, and this would be one of its components. We also have something called a left unitor, and it's another natural transformation. The eighth component of it goes from I times A, goes from I tensor product A to A. And so if you think about what this means in set, well, in set, the unit is going to be the singleton set. So let's say it's the set which just has one element that we'll call star. And so I times A, that's going to be a sort of pair like an element. And so an element of I times A, that's going to be something like star comma little a. And we can just change that to little a, just rubbing out this redundant star thing here. And that's kind of what our left unitor would be doing if we're looking at set as an example of a monoidal category. And we similarly have this sort of right unitor, which sort of gets rid of a unit on the right hand side. And so we have this sort of data, which is really what a monoidal category consists of, and we want this data to satisfy certain conditions. In particular, we want alpha, lambda, and rho, the associator, left unitor, and right unitor. We want those all to be natural isomorphisms, so these would be describing their components. They have to satisfy this naturality condition. These components have to be isomorphisms. And we also want a couple of extra conditions to be met, sometimes called coherence conditions. And basically that is to say that this diagram has to commute and also that this diagram has to commute. Now I'm not going to focus too much on these coherence conditions. I mean, you can always go back and pause the video and think about what's going on. If you want to sort of get your head around these coherence conditions. Also, I mean, what the coherence conditions are there for in a rough sense, is basically we have this kind of way of doing the sort of product of pairs of things in a monoidal category. But what about if we have 3 things or 4 things and we want to sort of product them together? Well, we already know that we can sort of translate between these different ways of thinking about the product of 4 things using things like our associator. But what we really want is that these different ways to transform the forms of our kind of products and so on are different kind of transformation routes that would go, say, from here to here, like this way or this way, end up basically being equivalent or equal to each other. So we say that this diagram commutes. That means going this way around the diagram yields the same result as going this way around the diagram. And similarly, we say that this kind of triangle has to commute. And it turns out that those conditions are sort of enough to imply that pretty much all the usual ways you think of changing between these kind of products of objects, if we have sort of 2 ways of doing it, they end up being kind of equal. That's a very rough kind of hand-wavy way of thinking about these coherence conditions. There's actually, my personal opinion is that you can spend a real long time thinking about these coherence conditions, but there's another concept, which is the idea of an unbiased monoidal category, which you can Google. And that's a sort of other version of this concept where you can kind of tensor product like more than 2 objects together at a time and so on. And if you think about that concept instead, you can sort of sidestep this whole kind of coherence thing. Anyway, let me now talk about the kind of my favorite example of a monoidal category, which is this example of this category set. So the objects are sets, the arrows are functions, our tensor product is just Cartesian product, and our unit is just the singleton set. So I've already sort of argued that that's kind of like a monoidal category, but one thing we ought to be able to do then is that if we have an arrow f from a to b, or in this case a function f from a to b, and a function f dash from a dash to b dash, we ought to be able to construct a function from a times a dash to b times b dash. So how do we do that? And in fact, we can describe how to do that more generally, okay? So it turns out, in fact, that if we have any category where that category has a terminal object, 1, and the categorical product is defined for any pair of objects, it turns out that we can think of that thing as well as being an example of a monoidal category. So we can think about this more general case, okay? So we have some kind of category with all these products and things. So how do we then think about what the kind of product of a pair of arrows is going to be? Well, what we can... Well, let's just think about this. We know we're going to have these projection arrows, so pi1 from a times a dash to a, and pi2 from a times a dash to a dash. And so then we're going to have this sort of pairing. And so we know that this arrow, f after pi1, goes from a times a dash to b. And this kind of arrow here, f dash after pi2, goes from a times a dash to b dash. And so if we just then take the sort of pairing of these 2 arrows, f pi1, f dash pi2, then that's going to go from a times a dash to b times b dash. So we can do this in set, but what does it mean? Basically in set, what this means is, well, we start off with a little a, well, let me use a different color. We start off with a little, so what does this mean in set? Well, it's pretty simple. We start off with an element of capital A, let's call that little a, and we also have a little a dash, and then we just do f on little a, and we do f dash on the a dash. So we end up with this pair of a f of a in b and an f dash of a dash in b dash. So that's kind of the idea. You can also, I think it's kind of interesting, you can also use the coproduct. If you have a category C where every pair of objects have a coproduct, so we have this kind of plus operation, and we also have an initial object 0, then those three things also can be thought of as forming a monoidal category. So this is really a very kind of general idea. Okay, so now we know what a monoidal category is. It's pretty easy to define a symmetric monoidal category. And so, roughly speaking, a symmetric monoidal category is just a monoidal category where we can switch the kind of order in which we tensor product together two objects. So, to be more precise, it's a monoidal category where for any pair of objects A and B, we have this kind of arrow, which is sometimes called a braiding arrow or a swapping arrow or a switching arrow, which goes from A tensor product B to B tensor product A. And such a thing has to be an isomorphism, and the collection of all such arrows has to form a natural transformation. So basically we have this kind of braiding natural isomorphism. And there's also a few kind of coherence conditions that we want to be satisfied. So here are the sort of diagrams. The most notable one, I think, is this one here, which basically says that if we swap A and B, and then we swap B and A, then that basically yields the identity arrow. So doing this and then doing this is like doing nothing at all. So it's sort of like if we start off with A comma B, and then we switch them round, so we get B comma A, and then we switch them round again, we get back to A comma B. So this is something that would happen in the category set. Indeed, this kind of category here that I was talking about before, where we use the Cartesian product as our tensor product and we use set, well, this isn't just a monoidal category, this is indeed a symmetric monoidal category. Actually, quite a few kind of monoidal categories that one encounters turn out to actually be symmetric monoidal categories. Now, one of the reasons we like these is because we can draw these lovely wiring diagrams of what's going on in symmetric monoidal categories. In fact, really the fact that set is a symmetric monoidal category is why I could do all that stuff with the apple crumble at the beginning of the video. But more generally, if we have a category C and we have a categorical product and a terminal object, then again, that's not just a monoidal category, it's a symmetric monoidal category. And that's because, in general, we can sort of define this kind of braiding operation as this kind of pairing of these two projections, pi2 and pi1. But yes, strictly speaking, yes, if we're being precise about things, then a symmetric monoidal category is going to be a monoidal category with this kind of braiding natural isomorphism, and we want to have that each of these three diagrams commutes. So I'll just quickly show these on the screen, and then again you can pause the video and think about these kind of things. These are the sort of coherence conditions that we want to be met. Okay, so now we've got this idea of symmetric monoidal categories under our belt from a sort of abstract point of view, we can really make connection with this idea of wiring diagrams in a very sort of concrete way. And so basically on the left hand side, I'm showing how we'd normally kind of draw stuff using the normal kind of graph-like visualizations of category theory, whereas on the right hand side I'm visualizing the same kind of thing with this kind of wiring diagram graphical language. And so on the left, our sort of objects are just sort of dots, or sometimes we just write the letters, but we're really thinking of them as dots or drawing them as dots. And our arrows are directed edges, really. Whereas on the right hand side, our objects are now becoming wires and our arrows are becoming boxes. So I'm reading these diagrams from the top down. And so this is saying that F is an arrow from object A to object B. And we're saying a similar thing here with the wiring diagram. Now, since we have this symmetric monoidal category, we are going to have this sort of unit object. And this unit object kind of has the property that, in a sense, timesing stuff by the unit object doesn't really change things. I mean, this is what happens in monoids, and it's kind of what happens in monoidal categories as well. So if we do the tensor product of an object with our unit object, it doesn't really change anything. And so in a sense, you could almost say that the unit object is irrelevant. And in fact, we tend not to draw it in monoidal categories. I mean, we can draw it. We can have a wire that we can label as I if we like. But it turns out that if we just don't draw it, then it kind of makes sense. We'll see more of this happening later. Okay, so another thing is that, let's say we have an arrow that comes out of our unit object. So for example, in the category set, our unit object is going to be this singleton set. And so if we have a sort of value of type A, or a value in this set A, then that's going to be a sort of element of this set A, and there's going to be a sort of corresponding function from this singleton set to this set A, which is pointing out, let's say, this element P of set A. Now, the way that we draw this in a wiring diagram, we have this sort of unit object up here, so this would be I, but remember, we don't have to draw that. So we can just think that we have this sort of box, which is, or this sort of arrow. So we just sort of think that we have this kind of box P, which is just sort of making an element of type A, if we like. So essentially, we can kind of apply this kind of translation, but then we neglect to actually draw the wire for. But then we sort of neglect to draw the wire for. But then we sort of neglect to draw the wire for our unit type. So I'll show an example of this momentarily. Now, the really important thing about wiring diagrams is that when we have the sort of product of a pair of objects, we can draw that in our wiring diagram by putting our wires side by side in parallel. Okay, so there's this idea that basically the tensor product of stuff can be represented by drawing things in parallel. Okay, so you could almost say that in a monoidal category, or a symmetric monoidal category, in addition to having this sort of sequential composition where we do one thing after another, where we compose arrows head to tail, we can also kind of have this idea of parallel composition, where we do things in parallel. So here we have this object A and this object A dash, and we can draw this in our picture by just putting these wires side by side. I mean, we could also draw the situation like this if we wanted. We could have a single wire for this object A times A dash, and then we could say G is an arrow from that to C. But this kind of picture is often preferred because we're sort of breaking things up in a more sort of atomic way. And so just as we can have parallel wires, we can also have parallel boxes. So if we have an arrow F from A to B, and we have an arrow F dash from A dash to B dash, well, we can represent this situation in a very sort of pleasing way like this. So if we look at different kind of horizontal slices of this, we can see what's going on. So here we have this object A times A dash, and here we have this arrow F times F dash, and then the output is going to be the B times B dash. Now, another thing that's really interesting here is that we can sort of shift the vertical positions of these things. So we could move this arrow down here a little bit. So the thing is, if we draw any sort of box in this, then we can think of that as being another arrow. So this box I've drawn is basically identity of A times identity of A dash. So we might draw it like this over here. So this kind of arrow isn't really doing anything, and that's what we've got going on here. It's not doing anything. But we could then draw this kind of box like this, and we could say, well, this is an arrow, which is F times identity of A dash. And then what we're doing is, after that, we're doing this arrow here, which is identity of B times F dash. And it turns out that that composition is always going to give us F times F dash. That follows by the sort of functoriality of this tensor product. So basically what I'm saying is that the kind of things that are suggested to us by this kind of graphical language of these wiring diagrams, the idea that, you know, we could sort of freely shift these boxes up and down the wires, and stuff like that, turns out to very, very nicely reflect the actual rules behind these symmetric monoidal categories. So let's carry on. Another thing is that we can have these identity arrows. I've already talked about this. So here we have this identity arrow. Think about this in set, for example. It takes in a value from set and returns that value. Well, we can just think about this as the absence of a box, or we could just draw a box around this, but say, well, it's not really doing anything because this identity arrow isn't really doing anything. We also have this sort of associativity up to isomorphism. And so basically, because when we have kind of these three wires in parallel, because of this kind of isomorphism, it doesn't really matter if we think about this as one wire followed by two wires, or kind of two wires followed by another arrow. Well, again, kind of what we would interpret from this kind of picture naturally, and how we'd naturally ignore this kind of way to separate out these three things, is kind of reflected in the rules of our symmetric monoidal category. In a similar kind of way, we have these sort of unitor things, these natural isomorphisms. And what this unitor kind of isomorphism is saying is that if we're going to time something by our units, then in a sense that doesn't matter, because I times A is going to be isomorphic to A. So we could think, oh, well, we've got a sort of unit wire here on the left, but we don't even draw the unit wire. And that's kind of reflecting how it's sort of, in some sense, irrelevant, because like timesing by the unit on the left just yields something isomorphic. And indeed, timesing by the unit on the right yields something isomorphic as well. Now, another very cool thing is that when we have a symmetric monoidal category, that means that we're allowed to sort of draw our wires crossing over each other. So if we draw a sort of box like this, then we could really call this box sigma A comma B, or call it swap if you like. It takes in something of type A times B and it returns something of type B times A. So this is really our kind of switching operation. And if you now look at the sort of coherence rules which we've thought about already, you can see that a lot of them are very naturally kind of suggested by our graphical language. Okay, so for example, this kind of rule here, which says for our symmetric monoidal category that if we do two kind of swaps, then that's just going to give the identity. Well, it's kind of like if we cross over these wires and then we cross them over again, we could sort of pull this tight and we just end up getting the original wires back again. So this is kind of like the identity arrow of A times B, or identity of A, tensor product identity of B. It's the same thing. So hopefully you can see that this is a really, really powerful kind of graphical language. And there's really a remarkable collection of different applications this has. So there's a wonderful video, I shall put a link to in the description. It's called something like Symmetric Monoidal Categories of Rosetta Stone. It's a video by John Baez where he goes through lots of examples of these symmetric monoidal categories. I mean, they're applied to think about all sorts of things in physics, like, for example, circuit diagrams and things in quantum mechanics. It turns out that there's this category of Hilbert spaces, which is a symmetric monoidal category. So there's, in fact, there's some researchers, I think it's Bob Koch said, or I heard he said, that if you teach like children how to manipulate symmetric monoidal categories well, and they can learn it easily through this kind of graphical language of wiring diagrams, well, they can end up being sort of more proficient at certain aspects of like quantum mechanics than, you know, seasoned PhD holding researchers, because, you know, if you know about this graphical language, you can sort of directly apply your kind of visual cortex to solve lots of these kind of problems very kind of easily. So let's just go through a quick example just to make sure we've got the idea. So this is a kind of arrow in set, which takes in two numbers, and then it adds one to the first number, and then it times these two numbers together. And so what we can do then, we can kind of extend. And so what we can do then is we can kind of extend this diagram. So we could say put a 7 here and a 2 here. And then we'd be thinking that this up above, this is the unit, which is our singleton set. So we'd basically say, well, we start with kind of just our singleton set, and then we're pointing out the number 7 here and the number 2 here, and then we're going to add 1 to 7, which will give us 8, and then we're also going to input this number 2, and then we're going to times them together, so the output is going to be 16. And so we could say that this is going to be equal to this sort of picture here, where we just make 16 as a number. Okay, so I really think that these sorts of wiring diagrams I'm going to talk about today ought to be used to think about all sorts of different things, because they make life so much easier. And another thing that we can do with them is that we can use them for programming. And so I found this amazing piece of software called LabVIEW, which basically allows us to program in wiring diagrams. And given all the connections with category theory and given the sort of visual nature of this, I think it's a wonderful thing to be able to program in these wiring diagrams. And so I want to look at some examples of actually programming in wiring diagrams using this LabVIEW software, because I think that it's a because I think that this kind of visual programming style is extremely powerful, and I think it's actually going to change the way that people program in the future. Okay, so those who know about functional programming languages will realize that when you have programming to do, it's often a good idea to think about what you're doing as if you're working inside this category set, which has objects as sets and arrows as functions. But we already sort of know from our apple crumble example that the category set is a symmetric monoidal category, and that means that we can really visualize what's going on using these kind of wiring diagrams. And so that begs the question, can wiring diagrams be useful for programming? And I think the answer is an emphatic yes. These kind of wiring diagrams are extremely useful for thinking about programming. And so to illustrate this, I want to look at this example of doing multiplication by 2. Because if we just use these kind of wiring diagrams, then we get a really beautiful way to think about recursion and to think about how we can perform all sorts of really sophisticated computations. And so let me try and set the stage. We're going to work in the category set. Our product is going to be the Cartesian product of sets, just like in the apple crumble example. And again, our monoidal unit is just going to be this singleton set. I'll think of it as having a single element, which is called star. And so we have a symmetric monoidal category. And so we can draw these wiring diagrams. So we have these different wires. And so we have these different wires representing sets. All of these wires are representing numbers here, except this one I'm shading in green, which is representing a Boolean in this case. And so this is basically telling us how we're going to times our number by 2. And an interesting thing here is that this kind of definition of multiplying by 2 is actually a sort of recursive definition. Okay, so the easiest way to explain what's going on here is to write this in maybe a more familiar language. So what we'd be saying here is that if we want to times a non-negative integer n by 2, we want to calculate 2 times n. What we're saying here is that what we do is that we're going to output a 0 if n equals 0. Otherwise, we're going to do n minus 1, and then we're going to times that by 2, and we're going to add 2 to the output. So this is what we do otherwise. And so now I shall talk through how this timesing by 2 function works in a particular example, so we can get some sort of intuition for what's going on here. So it's given by this diagram here. So we start with a number, we want to times it by 2. So we copy that number. So let's let me give an example. We'll start with a 2, and we copy it. We get a 2 and a 2, and then we have this if statement. Now the way this works is this first entry is like true or false. So, and then the second end, and then we have these other 2 inputs. And if this thing is true, then we give out the first input. Otherwise, sorry, yeah, we give out this input. Otherwise, we give out this input. So, for example, if it's raining, then I'll use an umbrella. Otherwise, I won't use an umbrella. So if it's in that analogy, if this is true, we'd output this. Otherwise, we'd output this. So the way that this works in this case is that we take in our number 2, we copy it, and then we check if it's 0. It's not 0, so this would be a false. And that would mean that we're going to be outputting this as this. And so we'd be outputting 2 take away 1, which is 1, times 2, which is 2, add 2, which is 4. Okay, but it's a recursive definition because we'd be calling the times 2 over again. And the reason I mention this is because it seems that there's something similar going on when one's willing to do a particular action. One wishes to change the world, but also retain a memory of the kind of action that they wanted to carry out initially. And so, like, here's the example when we're timesing by 2. So timesing by 2 is sort of like the direction that we're going in. And then what this is saying is that, well, there's a little action that we can take, which is adding 2. And then we've got a bit of a way there, but we still need to times by 2 once more. And so now we have to look at this and we have to do work on this. So it's kind of like if I want to build a house, this is building the house, and then I have to lay a brick, and I still have to carry on building the house with all the bricks I have left. And so the brick is still there, and then I have to carry on building the house, and so I have to lay another brick, and so now I have to carry on building the house, but I have 0 more bricks to lay, so that's done, and so this is 2 plus 2 plus 0, and it's finished. And so there seems like there's a parallel here between this kind of recursive definition of timesing by 2 and the idea of something to do with maintaining will. But before I make that connection, let's just make sure let's go through this diagrammatically because it's kind of fun. So we start with 2, we want to times it by 2. So we want to do this. Now, if we're going to copy the 2, then that's basically like this. 2 minus 1 is 1. So it becomes this. And we can see that this is not equal to 0. So this is going to be false. And since this is false, that means we're going to be doing this second thing. So we've got this now. And so now we want to do 1 times 2. And then we've got to add 2 to the end. So now the question, so now we're doing this. So the question is, what's that become? And so our full result is going to be this. And so again, we're copying the 1. One minus 1 is 0. We know that 1's not equal to 0, so this is just false. And since we're working on a false, we've now got this. So now we want to do 0 times 2, add 2, add 2. So we can just write that like this. And so let's work out that. Okay, so now we've got a 0 here, and then so we copy it, got a 0 here, and a 0 here. Now this is equal to 0, so this is true. And that means we do this y here, so all this if statement just becomes this. And so it's just 2 plus 2, which is just 0 plus 2 plus 2, which is just 4. And so now we've seen how we can use things like if statements and recursive definitions. And so it's kind of clear that with this sort of wiring diagram based language, using the ideas of recursion, we can encode all sorts of ideas to do with programming. Now, I think there's a couple of interesting things to say here. One of them is something that I sort of noticed after a very interesting, one of many very interesting conversations I've had with my friend Jos Hoebe, and he was talking about the idea of free will and the idea of willing oneself to complete an activity. So Jos Hoebe is a very creative geometer who has all sorts of interesting ideas to do with spirituality and philosophy as well. And one of the things that he was saying to me was that when you're trying to will something to happen, it's important to maintain, it's important not just to perform the activity, but also to maintain a sort of memory of the fact that you wish to complete that task. And it seems to me that there's something very similar going on with this idea of a recursive definition. And so when we're timesing by 2, as we sort of keep going around this loop, we're sort of reducing the amount of work we have to do. So when we take away 1 here, that means that we're not going to have to times by 2 as much. We're getting closer to our goal. And we actually do the work by adding the 2, but we also have to keep willing ourselves to repeatedly revisit the formulation of the original problem. And I suppose you could probably make a sort of variant of this where you're talking about more general tasks, and instead of writing times 2 here, you could write something like this is willing oneself to continue performing a particular activity. Now, another thing to say here, and this is another great thing about thinking. Now, another thing to say here, and this is another great thing about category theory and the abstractions, is that when we're drawing all of these wiring diagrams, you could think, well, we're just talking about functional programming. We're just talking about sets and functions. But what about if we're not? Instead of working in this category, which has objects as sets and arrows as deterministic maps, deterministic functions, we could instead work in the category stock or the category fin stock. You can look these up. And in these kind of categories, sometimes they're called categories of stochastic map. And in these kind of categories, which are sometimes called categories of stochastic maps, well, the objects are still basically sets or maybe structured sets, but the arrows are now these kind of stochastic maps. And we can basically think of those as something like functions, but whereas a function takes an input and it outputs a value deterministically, a stochastic map, roughly speaking, takes a value as an input and it outputs something like a probability distribution over the different outputs. Okay, so you can imagine, for example, a stochastic map sending different varieties of apple to colors. And so if you put a golden delicious apple in, then maybe there's a certain probability that the color of that would be green, and there'd be some other probability that the color would be brown. And if you put a different variety of apple in, you might get some different sort of probability distribution over the different possible colors. And so basically there's a whole plethora of different symmetric monoidal categories that you might want to interpret a particular diagram in. And indeed, if we think about this idea of doing recursion in terms of, let's say, this category of stochastic maps, then it could be a similar situation, but maybe all of these things are not deterministic functions anymore. And if you try and connect that again to the idea of free will, it's kind of interesting, because then you might have a case where one is sort of trying to repeatedly perform an operation, but maybe there's some kind of randomness in there based on like what kind of outputs they get. And so there might be some kind of random aspect to whether somebody can complete a task that they've started. I mean, I know a lot of people that have started big projects and then for some kind of random reason, they haven't actually followed through and completed the project. Okay, so I've been trying to explain why I think that wiring diagrams are really useful for thinking about things in the real world. And so now I want to show you some software that allows you to program using wiring diagrams. And it's difficult for me to convey how amazing I think this is. I think it's so extraordinary because I think that wiring diagrams are so well suited for our kind of minds, our visual cortex and things like this. And it's so great to be able to program using wiring diagrams. So this is this software called LabVIEW. Let's boot it up and I'll show you how easy it is to program using wiring diagrams. So let's create a new project. So you can download LabVIEW easily. We'll create a blank thing. And so we get these two windows here. And then like there's so many things you can do with LabVIEW that I'm not touching here. I'm just showing you a sort of fairly restricted example, but we'll go on this front panel here. Let's make a numeric control so we can put a number in there. And then we're going to have another thing, which is a numeric indicator. And so now on the right, let's start to have some fun. So we can get this plus box here and a wire that comes out of this numeric thing. This is going to be of the type number. And then if we right click on this box, we can say create a constant, let's say 2. And we can move these wires around as we wish. And then we can have this wire coming out. And now let's have another box, multiply. And we're going to multiply by 5. And so we have to wire things up properly. And now let's display the output. And there we go. We've just written a computer program. And so if we put 3 in and we run this, then we're going to add 2 to that. So we'll get 5, and then we're going to times that by 5. We should get 25 as our output. So if we just press run, yes, indeed, we do get 25. Okay, so in the previous example, the only kind of wire that we used was representing numbers, and it was a quite sort of straightforward linear example. But there's another thing that we can do with these wiring diagrams, which is to describe recursion. And I think that this is really interesting from a sort of mathematical point of view, but it's also, I love it from a sort of visual learning point of view, that we can make these kind of wiring diagrams involving recursion, and we can also include those within our system. So let's have a quick go with that. So let's see if we can make a function that's going to times by 2. So we're going to sort of cook up this function on the right here. So let me just start by grabbing the different sort of boxes that we're going to need. So we're going to need this decrement function. This takes in a number and spits out that number -1. We're also going to be a bit sort of self-referential about this. So we're going to drag this box down here, and this is actually going to represent the original process. And now there's some stuff we have to do with that later. We're also going to use this increment box, which takes in a number and outputs 1 plus that number. We're also, let's have another copy of that. Now we're also going to need some booleans. Now boolean is just something that's true or false. And so we're going to get this function here, which it takes in a number, and if that number is 0, it outputs true, otherwise it outputs false. And we're also going to want a numerical constant, which is going to be 0. Now, we're not just using a wiring diagram here, we're also going to include the ability to copy. Now, another kind of box that we want is something that copies its input. So think about a function where you put in an input and then you can get a pair. And then finally, we're going to want this kind of select box here. And this is basically going to allow us to do something like an if statement. So now let's just wire this whole thing up. So we're going to take our input, this is the number that we want to times by 2, and let's start by plugging the wire into here. Now another thing that we want to do is we want to actually copy this input number. So if we right click on this wire and then we click create wire branch, then we can plug into here as well. Okay, so essentially you can think of this dot I've just made as a new kind of box. It takes in an input and then it spits out 2 copies of that input. So this is sometimes called a copy operation. In fact, there's a special kind of symmetric monoidal category which is called a copy delete category or a copy discard category, where you're allowed to do these copy operations. And there's another discard operation where you take a wire and then you terminate it, or you make it change into the monoidal unit. And so we can imagine that we're dealing with that, but we know what's happening in terms of set theory anyway, because in this case we're working in the category set. Each of these wires is just representing a set, and we can take an element of any set and then we can output 2 copies of that element, and that's kind of like what this orange dot is doing in this case. Okay, so now we're sending this number into this is equal to 0 question mark box, and what we're getting out is a Boolean, and we're going to put this into our selector box over here. So notice that this wire is green because this wire is not of type number, it's of type Boolean. It's either true or false. Okay. The next thing we want is something that we're going to do if this green wire is true, and in that case we want to be outputting 0. So this upper blue wire is the output when this green wire gives true. And then the other thing we need to do is what's going on if we get a false. So if we get a false, in other words, if our number is not 0, then what we're going to do is we're going to take away 1 from our number, and then we're going to call the whole times 2 function again. So now we have to do some kind of manipulation here. I'll just say what we do. We click up here, and then we say that's the input, and then we click down here, and then we say that's the output. And now we're allowed to wire into this box and wire out of it. And this little grayed out box here, this is, we can sort of think of it as a kind of copy of the whole big box that we're making. So it's a sort of recursive, okay? And then after we've done that timesing by 2, indicated by this grayed out box, we're then going to add 2 by doing 2 of these increment things. And this is going to be what we do when our input is not equal to 0, okay? And then this is going to be our final output. So there you have it. This is basically a wiring diagram that should do this multiplication by 2. The way we'd say it in words is that we take in a number. If that number is 0, then we output a 0. Otherwise, we take 1 away from that number and we times it by 2, and then we add 2. Okay, so this is a sort of recursive way of defining multiplication by 2. The only problem is if we actually try and run this, so let's change this to a 5, let's say, or a 7, or an 8 actually, and then we press run, we get an error. So at this point, if we were just doing pure mathematics, this would already work, and this would define for us this multiplication by 2 sort of operation. However, there are some extra things we need to do in LabVIEW because of the way it's set up to make this actually work. So firstly, we need to click here and go to VI properties, and we need to go to execution and change this to shared clone reentrant execution. Okay, and you can see that this is no longer blacked out now. But even so, if we try and run this, so let's put a 3 in and try and run it, we get a complaint. And basically that's because I guess LabVIEW can't figure out that this is actually going to terminate, that this is a sort of well-defined recursive thing, because it has to do with the details of when the thing's equal to 0 and what's the input and all the rest of it. So LabVIEW complains that this looks like it's going to take an infinite amount of work to go. But this is easily fixed. We just have to make sure LabVIEW understands what the kind of cases are that it has to deal with. So if we right click and then we go structures, we can make a case structure. So this is an interesting sort of construct. It basically acts in different sorts of ways depending on its input. So firstly, we want it to know that we're going to be dealing with numbers. So if we make a numeric constant and put it here and then wire it in, then basically what this number at the top is doing, what this value at the top is doing is this is the sort of value. So basically the idea now is that we have this sort of value at the top, and based on what this value is, which is representing the input value, the nature of this box can be different. So the way we want to set this up is that when the input is actually a 0, we just want to output a 0. So if we right click here and then we go numerical constant, and we'll put a 0 there. And we want this to be the output in the case where the input is a 0. That's fine. And then the other case would be what we do if we have 1 or greater. So we write that as 1 ... And in this case, we want to do something different. So in this case, where the input is 1 or greater, we actually want to be using this stuff up here. And now actually we don't want our input to be 0. We want our input to be branched off from here. So we go create wire branch, and then we're going to plug it up like that. So now basically we've just got this case construct, and this helps LabVIEW to know that the kind of entries that it's dealing with are well defined. In this case where we have a 0 here, we need to tell LabVIEW what to do. So in this case, we're going to make a numerical constant of 0, and that's what we're going to be outputting like so, and we're done. So basically now we've got these two different cases. We've got that when the number that we're inputting is a 1 or more, I'll have to connect this wire. We're going to be taking away 1 from it and then calling the procedure again and then adding 2. Otherwise, in the case where the input's 0, we're just going to be outputting a 0. Now, actually, this second case is the thing that we generate from this is never actually going to get used because of this selector up here. So this is sort of like an extra thing we need to do because we're dealing with an actual programming language rather than like pure mathematics. Anyway, let's actually run this now and see if 2 times 3 is indeed equal to 6.